All right, welcome to our last video of Unit 6. These are talking about electrolytic cells. Yay. So, in the case that our cell potential is not enough to drive our reaction, electricity can be used to power the reaction. Now, you know that because that's how most things in life nowadays, at least, are powered. But we just got finished talking about times where sometimes the cell potential is positive. So it's like it's enough to power it. However, many times it's not. Thus, we use electricity. So an electrolytic cell is a cell in which a process driven by an outside source of electricity occurs. These reactions, therefore, are called electrolysis reactions. Now, this is different from a voltaic cell, in which basically it makes its own power. Electrolytic cells need power. It's kind of what it comes down to. That's not quite the only difference between them, but it works for now. So an electrolytic cell typically consists of two electrodes immersed in the same solution, or sometimes actually molten salt. They'll actually take a salt, kind of melt it down, then stick things between it. Typically, though, we're just going to think of it as the same solution. But there's no salt bridge between them. Then typically the power source connects the two electrodes outside the solution by a wire. So this is you've got something and you stick two electrodes in it and you attach alligator clips to them to a battery. You know, this is you sticking a battery to random things. That's electrolysis. So, for any half reaction, the amount of substance reduced or oxidized in an electrolytic cell is directly proportional to the number of electrons passed into the cell, meaning the more electrons you pass in, the more stuff you're going to actually reduce or oxidize. Now, keep in mind that electrolytic cell is mainly two words, electro and lytic. Electro refers to electrons, electricity, etc. Lytic, think back to biology, the term lyse. This is more breaking. So electrolytic is typically a cell in which you use electricity to break things down. The more electricity that you put in, the more stuff you can break apart. So the quantity of charge, referring to how many electrons, of 1 mole of electrons, as measured in coulombs, is 96,485 coulombs, which, by the way, is the same as Faraday's constant. Now, a coulomb, let me actually define that, is the quantity of charge passing through any point in a circuit in 1 second when the current is 1 ampere. Now, second is the time, ampere is a measure of current. So a coulomb, again's definition, is the quantity of charge passing through a point in a circuit in 1 second when our current is 1 ampere. Now, that's kind of the basis of electrolysis type reactions they're going to ask you. Typically, they're going to basically say, all right, we have this reaction, we throw this much current at it, what are we going to get out of it? So, coulomb, 1 second per 1 ampere. Or in summary, coulombs, change it around a bit, will equal the amount of amperes we have times seconds. Base says you're going to get this much charge if this is your rate and it's done for this long. Okay? Coulombs, amperes, seconds. There you go. In a unit phrase, this is typically A times S, in case you'd like to know. Okay. Let's calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amperes. So, as usual, actually, no, I think on this one, I'm going to actually work you through this with you guys. I've actually even had issues in the past. Really doable. But first thing we want to do is get our coulombs. Now, coulombs will equal amperes times seconds. Okay, if we have 1 hour, I'm pretty sure you can do the math. That is 3,600 seconds. Okay, we have a current of 10 amperes, so we want to figure out how many coulombs that'll be. So that'll be coulombs will equal 10 times 3,600, which gets you 36,000 seconds. I'm sorry, not seconds, coulombs. Dang it. Coulomb, 10 times 3,600, which equals 36,000 coulombs. All right. Now that we know our coulombs, we can actually convert to moles of electrons. And that'll come in handy very soon. So we have 36,000 coulombs, and we know that 1 mole of electrons is equal to 96,485 coulombs. Multiply that, and we get 0.373 moles of electrons. So that says that if we do that for 1 hour with a current of 10 amperes, that we will get about 0.373 moles of electrons actually thrown into this reaction. Now our question then is going to be basically, all right, well, how many grams is that? Well, somehow we have to relate electrons and grams of aluminum. Well, that's kind of weird, except if you remember, we have a chart of standard reduction potentials. On those charts, we have various random reactions, specifically one including aluminum, and that reaction happens to look like this. Al 3 plus 3 electrons produces Al as a solid. Now, while this doesn't actually normally look like a normal equation, it actually is. Because notice, we can use this to go between electrons and grams of aluminum. So, that's what we're going to do. And yes, this comes down to stoichiometry. So that gets us then 0.373 moles of electrons times, I'm actually going to erase this a bit, so write what you need, pause if you want, but I'm just going to kind of erase this in just a second. Okay, so that is 0.373 moles of electron times 1 mole of aluminum over 3 moles of electron, and then to grams will be times 26.98 grams of aluminum over 1 mole of aluminum. Multiply that together, and you get 3.36 grams of aluminum. And there you go. Not too bad. That's electrolysis. That says if we shove a current in for that long, that's how much aluminum we should be able to actually scoop out of that reaction. Typically, this will... No, that's really much it. So there you go. That's electrolysis. All right. So we got another question. We're trying to figure out how much time is needed to deposit 1 gram of chromium metal from an aqueous solution of chromium chloride using a current of 1.5 amperes. Okay, similar process as before. You're just, you're solving for time this time, not quite grams. So I'll give you a few minutes, try it, and then come on back. All right. So in this case, we're using chromium metal and chromium chloride. So the thing you gotta notice is that chromium chloride, we don't have any reaction on our sheet using chromium chloride. However, we're somehow trying to go between chromium metal and chromium chloride. Notice they said aqueous solution. Aqueous solution typically implies it's going to be ionic compounds are going to split up. Well, if you were to split this up, you'll find that you get chromium 3 plus and technically 3Cl minus. So that means that we're looking actually for a reaction that somehow is going chromium 3 plus to chromium as a solid. And in that case, we're going to add 3 electrons. So that is actually on our chart somewhere. So we're going to actually end up using that. So we need 1.0 grams of chromium. By the way, that's the solid metal. We need to go to moles of chromium. Our molar mass is 52.00. Once we're in moles of chromium, we can go to moles of electrons, and that will be 3 moles of electron for every 1 mole of chromium. All right, once we're in electrons, we can go to coulombs, and then from coulombs go to time. So that means 1 mole of electrons is 96485 coulombs. We're almost done because we know that. All right, So when you multiply those out, they'll get to Coulomb. And then what we're going to do is plug that into our ampere and second equation. So put those in your calculator, a little bit long, but you get 5566.4 coulombs. Okay, and we know that our equation is that coulombs are equal to ampere times second, which means might as well just kind of add that into our equation. So that will equal 1.5 ampere times our seconds. Okay, divide both sides by 1.5, and you get that that will take you 3,711 seconds. Now you can get that into minutes if you want, or just leave it. If they ask you for minutes, put in minutes. But that's your answer. Again, we went from grams to moles, moles to electrons, electrons to coulombs, coulombs to seconds. There you go. That's electrolysis.